Hello students, today we are going to start the last chapter of your course, and the last chapter contains nuclear reactions, reactors, accelerators and detectors. First and the foremost thing is that what is a nuclear reaction. So for example, when two nuclei come close together, a nuclear reaction can occur that results in nuclei being formed. And nuclei are, as we know, that the nuclei are the positively charged, and the repulsion between two nuclei keep them apart. If this is a nuclei, this is another nuclei, then both are the positive one. This is also a positive nuclei, this is a positively charged nuclei as well. When they come close together, then due to the repulsive force between them keeps them beyond the range, some certain range where they can interact unless they are moving very fast and penetrate that nuclear range and that repulsive range. So for example, in sun and stars, whose temperatures, internal temperature range is between millions of Kelvin, many nuclei present inside them have high energy and high enough speed for the reaction to be frequent. In lab, we can produce nuclear reaction as well on the small scale, either with some particles like alpha particle with proton, neutron and heavier nuclei accelerated in various ways. Okay, so for example, we did discussion on nuclear reactions throughout our course, but we never focused that what are the fundamentals required for the process to happen or the reaction to happen. Now there are some things which need to be conserved, like charge should be conserved, atomic mass should be conserved, atomic number and neutron number should be conserved throughout the process. Energy should be conserved in terms of mass and energy, and your total angular momentum should be conserved, something like this. So we are going to discuss these things in a little deep manner. Okay, so let's start. If I focus here now, now for a nuclear reaction, like this is your reaction in which nitrogen with the alpha particle converting into two different nuclei. Okay, they came close together, or however in any significant way this nuclear reaction can happen. We have many number of ways to have a nuclear reaction. Okay, so the next thing is the types of nuclear reaction, under which reaction this reaction comes or another reaction comes. We are going to discuss that. Okay, so for types of nuclear reactions, first of all, the two things come in mind, that the reaction is elastic or inelastic reaction, or the elastic scattering or the inelastic scattering. Now in particular, in elastic scattering, the same particle are scattered in different directions and there is no loss of energy. Okay, these are the two things. The particle which are interacting as a product nuclei, the same particle will be there as the reactant nuclei, and there will be no loss of energy. Now we discussed this reaction very well in our initiation of the course. When alpha particle is the alpha scattering, when alpha particle strikes the gold foil, and alpha particles does not lose any energy, or generally what happens that they change their direction of motion. So here in this type of reaction, the incident particle strikes the target nucleus and leaves without any loss of energy. Okay, and in general with changed direction of motion. The most familiar example is the Rutherford alpha particle scattering. Okay, some different example we can have, and these kind of reaction can be written as, like if I do react a particular scattering, if I propose a particular scattering like neutrons by the graphite, so we will write that reaction as These two are the reactant and these two are the product as well. Okay, like this reaction where this is the target nuclei, this is the target nuclei, and this is the striker on the target nuclei, and we are getting the same results. Okay, now the next thing is, the main thing in this elastic scattering is that the same particles are scattered in different direction and there is no loss of energy. And the next thing is that the residual nucleus is the same as the target nucleus and is left in the same state, like in ground state as the latter. Okay, so this is the residual particle here, and this is the residual particle is the target nucleus. So this is the target nucleus, and this is also the residual nucleus, means the product nucleus, means the daughter nuclei. Okay, and they left in the same state because there is no energy transformation between this and this, as they do not lose any energy conservation happens here, as they do not lose any energy. So this happens, these two happens to be in the same state. As if initially this state, the state of this daughter nuclei was ground state, then the final must be the ground state as well. Okay, then the next reaction is next type of reaction is inelastic scattering. Now in inelastic scattering, the same particles are scattered in different directions with the different energy. Now they lose some energy, as there is a loss of energy due to collision. They lose some of their kinetic energy, and the residual nucleus, which is the same as the target nucleus but is left in the excited state, so that the process can be, I can represent my process as, if this is the initial target nucleus in which we are bombarding some kind of another, like for example here lithium is the target nucleus and we are bombarding a hydrogen atom, a proton, more precisely. Then we are getting lithium, the same nuclei, with respect to the same proton or hydrogen atom. But the main thing is that this nuclei is in the excited state because this particle actually transferred its kinetic energy to this. That's why the kinetic, it loses some kinetic energy and it gains some energy. Because of this gain in energy, this lithium is left in the excited state, and star is the representation of that. Now like I can write this reaction as xy and x star. Okay, now this is in excited state of x, and x is in the normal state initially. Now this is in excited state. Okay, so in such a reaction, the outgoing particle is same as the incident particle. Okay, and I can write my reaction something like this. Now there are some another reactions like disintegration, and this is the most general type of nuclear reaction, in which the nuclear particle is absorbed and a new particle is outgoing particle. Like for example, in disintegration, I have some disintegration process in which I need to bombard some particles, initial particles like protons, like deuterons, and like alpha particle and neutrons. Something like these are the bombarding particles. We will bombard this particle on particular target, and what will you get? That this target just transforms into a different nuclei, and the leaving particle, the bombarding particle, gets absorbed, or the new particle which is as the outgoing particle. Now this is the daughter nuclei and this is the outgoing particle. Then these outgoing particle will not be the same as the bombarding particle. Okay, for example, if I am processing a particular reaction in which I am bombarding a proton, then there are some cases that outgoing particle, when bombarding particle is proton, then the reaction can have be any one of the any one of these any one of these leaving particle, like for example, if I take this reaction in which lithium is bombarded with a hydrogen atom, and we are getting a new daughter nuclei and only neutron is coming out. Okay, here neutron is coming out, here is alpha particle is coming out. So we have some reactions, disintegration reaction. First is the type of with protons. If I do project proton on a particular target, then for example, if I take another examples in which I do the transmutation by protons, and I have a particular reaction in which, like if I write some another examples, like lithium is bombarded with proton. Okay, what I'm getting a particular state in which, like beryllium 8, and this is left in excited state, and then it's break into two different alpha particles. Okay, now however, this is the transmutation process. You're going to make something different, and you are getting something different results. Okay, so this is the same with these reactions, that you are bombarding initially proton and you are getting outgoing particle as different nuclei, and daughter nuclei is different than the target nuclei. Similarly with the deuterons, we can have outgoing particle as alpha particle, proton and neutron. So you have, more precisely, you have a particular bombarding particle, and you have three cases of outgoing particles, like alpha if with proton, alpha, deuteron and neutron. With deuterons, alpha, proton and neutron. Deuteron cannot happen here in the disintegration process. So with alpha particles, if you are bombarding with alpha particles like lithium with this alpha particle, you are getting boron plus some rage or okay, radiations. There are some another examples in which alpha particle is the bombarding particle, and proton and neutron are the outgoing particles. Okay, now you need to remember one or two example of each and every reaction. This is not a hard task, you can do, because we studied all these things in 12th class as well. So with neutrons, the same kind of reaction, the disintegration process in which a neutron is the bombarding particle, and there are some these target nuclei, and we are getting some daughter nuclei with respect to the outgoing particles. Now these are the outgoing particle with respect to these neutrons. And another one is radiative capture. Now radiative capture, we already studied electron capture in this in the last chapter. Now in this particular reaction, proton is absorbed, or a hydrogen atom like a low energy neutron or proton may be captured by the target nucleus. You are using a target nucleus and you bombard these particles and they just got absorbed. Then what will happen, you will get a new daughter nuclei and some rays, and because it happens to be that this transforms itself into excited states, and then comes out to a ground state, we use losing some energy. Okay, now next reaction is photodisintegration or photonuclear reactions. Now in the photodisintegration process, if we are bombarding the photons, high energy photons on particular target, then we are getting a different nuclei with respect to some different outgoing particles. Now the outgoing particles may or may not be radiations, but for the photodisintegration, we are using a particular nucleus in which we are bombarding very high energetic particles. Now for this reaction to happen, we need to have that the photon should have a greater energy than the binding energy of this composition. Okay, like for this reaction, the minimum energy for minimum photons energy required to be this 2.25 mega electron volt. Okay, these are, now next reaction is direct reaction. Our next reaction is direct reaction. In this reaction, the incident particle collides with the target nucleus and immediately pulls out the nucleons out of it, and it is called a direct reaction. So here we are using a particular, means immediately the main focus on the this term in this reaction is on this term, the immediation process. That when you strike a particular particle on these target nuclei, you get immediately some different result, and you are getting some outgoing particle with respect to the total nuclei. Okay, so this is the target reaction, and we can have a stripping reaction, means the inverse reaction of this. So inverse of this is, okay, this can also happen in which the projectile consisting of more than one nucleons is incident on the target nucleus, and it loses one of its nucleons to the target nucleus. Okay, the next reaction is fission. Now we already studied this fission reaction, in which the target nucleus, when it happens to be under interaction with the projectile particle or the bombarded particles, then it breaks into some smaller nuclei, and this is the fission process. Okay, like for example, uranium, when bombarded with a neutron, we get these as the daughter nuclei. Now the atomic number and atomic mass number of these are very far less than the parent nuclei. So these are the small nuclei, we can say, with respect to some neutron and energy as well. Okay, in the next lecture we are going to discuss conservation laws in the nuclear reaction, which are most needed, and then we will study the interactive process in terms of energy conservation. Okay.